Hello, everyone. I guess I have the pleasure of introducing Jared. He is the person that taught me everything that I know, or at least the foundations of starting everything I know. And so I've been very lucky to take my first data science class through with him. And without further ado, here's Jared, the one of the organizers of this event.
So I'm going to be talking about accelerating R code, dramatically speeding it up from something that takes forever to run, hours if at all, into seconds. This is going to be somewhat similar to a talk I gave at the first R conference 6 years ago. That was more of a survey. This will be more of a problem I had and walking all the way through it and all the different paths I took. So what was the ask? What were we trying to solve? What are we trying to accomplish here? Out of millions of points, which are similar to each other? Essentially, which points are within a certain distance of each other? It's a range searching problem. So what's the problem about this? What's the big deal? It's slow. And the question becomes, how slow is it? I want to quantify how bad this is in terms of calculations. So this problem takes n times n minus 1 divided by 2 calculations. That's a quadratic relationship. For 500,000 rows, that's 125 billion calculations. That's 125 billion slots in memory. For 1,000,000 rows, that's 500 billion calculations. I doubled the rows, but I quadrupled the calculations. The calculations are big O of n squared. And 1,000,000 rows really isn't that much data. So let's check out the data for this particular problem. This is just a sampling of about 500,000 points, and it's simulated data. The actual data set had millions and millions of rows. Now, each row only has 2 dimensions, which is nice. It's not a high-dimensional problem, it's 2 dimensions. And remember, we want to calculate how similar each row is to every other row. And then we want to find the ones that are closest to each other according to some definition. Visualizing the data, it looks like a Rorschach test, and we can see that there's more density in certain parts of the plot than in other areas. For my first attempt, I started with the obvious function, dist. It's built into base R, and it returns the distance between every pair of rows. So I call this function, and it did not go well. I don't know when it's going to finish. Crashed many sessions. So that didn't work. Had to go back to the data and look at it again. And I noticed something. When I looked at the ranges of the X and Y axes, I said something's up, and I summarized them. The first dimension goes from negative 100 to 100. The second dimension goes from roughly 5 to 68. And I said, you know what? That looks a lot like latitude and longitude data. And if it looks like that, maybe I can use the tools in the SF package to treat this stuff like their geometries. So I use ST as SF to convert the data into geometries, and I treat var1 and var2 as latitude and longitude. It's now like points on a map. They weren't points on the map. There's no reason we couldn't use that technology to work with it. So I decided, let's plot it on a map. And it looks like this blob trying to take over the Earth. Again, the map isn't really that useful because, the data aren't meant to be mapped, but I want to see what it looks like. So now that we're using SF, we can use a function from SF called stDistance. Now this is from SF, but it requires that the LWGeom package be loaded. And this measures the distance between every point and every other point. And I figure it's in the SF package, it's meant for geometry, it's going to be great. It was a bit of a dumpster fire, or rather a computer fire. It didn't finish. So I turned my attention to another function in SF, stIsWithinDistance. It's exactly what we want. You give it geometry points, and it tells you which points are within a certain distance of each other. Now, this function is meant to be used with meters. I know there's a new way to do it with latitude and longitude data, but it's very new. So I convert it into meters. So I'm taking my data, which I pretended to be lat long. I'm now converting that to be meters. I'm like 2 steps removed from the original data. And I had to convert my real threshold into meters, which was roughly 11,000, which was not exactly a one-to-one crossover, but it was worth a shot. So I run this, and once again, it didn't finish. I needed a new idea. So I go back to the data, which is still being plotted on a globe, and I could see physically that there are some points which are just dramatically farther away from other points. Like the far left is nowhere near the far right. So why am I comparing a point on the far left to the far right, or the far top to the far bottom? So I thought, let's split up the data into a grid. Let's break it up and analyze different sections of the grid separately. So continuing to use SF, there is a function, stMakeGrid. This takes the range of the data and evenly fills it with equal-sized boxes. These boxes can be squares, or in our case, hexagons, because they fit in better. Our goal is to get the grid cells small enough so we're not comparing too many points at once, but not so small that stMakeGrid has a tough time doing the computations to make the grid. So we visualize this now, and we can see that the points fall into individual hexagons. So now instead of comparing all the points, I'm just going to compare the points within a single hexagon. Assuming the points are evenly distributed, I now have G, the number of groups, times n divided by G times n divided by G minus 1 divided by 2 calculations. Because assuming that there's n over G calculations in each cell, I just need to look at each individually, and I do this G times. For 500,000 points and 600 groups, this is about 208 million calculations. That's roughly 125 billion fewer calculations than before. This assumes that the points are evenly distributed, which they're not, and we'll look into that. The difference is stark between not grouping and grouping. We're talking millions of calculations versus billions, hundreds of billions of calculations. But what do we do about the points near the edges of the hexagons? What if you had 2 points on either side of a hexagon border? What do we do about those? Because they wouldn't be compared, even though they might be right next to each other. So we inflate the hexagons. We use stBuffer to make each hexagon spill over a little bit into the other hexagons. This way I'm counting a little bit of the points outside the hexagon. Yes, some points near the borders will be counted twice, but we can remove those later. It's not that big a deal. The goal is we now have overlapping hexagons, so no pairwise distances get missed out on. And you make the buffer really small, just slightly bigger than your threshold. So if you plot it again, you can't even tell the difference because the buffering is so small you can barely tell the hexagons are overlapping. So now we need to find out which points fall within which hexagon. We do a spatial join using the stJoin function, and we say, find out exactly which points intersect, intersects, with which hexagons. It's beautiful that we can do this using SF, makes it really simple. We plot this again now, color-coding the points according to the hexagons. Remember, we're comparing points within a single hexagon against all the other points on a hexagon, not having to overlap. Well, the hexagons overlap, but we don't need to compare outside the hexagons. It's all done for us. Now, stMakeGrid and stJoin can be slow, and I'm trying to wring out as much speed as possible. So I looked into the hexbin package, which has an eponymous function. And this can figure out which points fall in which hexagons, and it'll make the hexagons much faster than stMakeGrid. But it doesn't actually give me the borders of the polygons, and it can't deal with these border issues. It can't create the buffer. And doing that after the fact might actually take more time. It won't be much faster overall. So this was a bit of a false start, and I just went back to the grid we have. So let's examine that grid. I want to count how many points are in each cell. So I drop the geometry, because if you count with the geometry, it has to aggregate the geometry, and it takes a lot longer. I get a count, and I remove any hexagons with only 1 point in it, because there's nothing to compare it to. So my hexagons now range anywhere from 2 to 100,000 points, with the median number of points in hexagon being 201. That meant the median number of calculations was 20,000, which is manageable. However, the biggest group still has 5 billion calculations for the biggest groups. That's a lot. But if we add up all these different calculations, we see we now have to make slightly under 14 billion calculations, as opposed to 125 billion. That's an order of magnitude faster. So now that the ID is labeled, we can split it up. So I first tried group nest, which will take the data frame, and rather than making a grouped tibble, it will make a list column of individual tibbles because I sometimes find those easier to reason about. I then use map inside of a mutate to iterate over that list column and apply my function to each of them. So I do this. I first transform it into meter so I could use st within distance. I do the group nest to break it up into a list column, and I call st is within distance on each of them. Our problem just went from impossible to solve to taking hours to run. If each group was small enough for st is within distance. So we have two issues. Group nest can be slow. It's actually a slow process. And st is within distance is slow and might not even finish. So we'll tackle one thing at a time. We'll first deal with group nest, then we'll deal with st is within distance. So instead of group nest, I use the combination of group by and group map. Group by creates, rather than a list column of tibbles, it creates a grouped tibble, and that is a faster operation. Then group map iterates over that grouped tibble and returns a list of results, sort of like dlply from plier. So I swap out group nest and I run this, grouping by cell, then I do a group map applying this st is within distance over each of the groups. We now went from hours to minutes, a dramatic speed up just by swapping out group nest for group map. If each group was small enough for st is within distance. And we could have made smaller cells, but that would have added computational time in the cell creation and the joining. So I thought I could still do better. And I turned to data table because it excels at grouping. So I take my SF object, I convert it into as.datatable. I then pipe that into square brackets because datatable uses square bracket notation. And you can pipe into square brackets if you put a dot in front of the square bracket. I group it by cell. There's a group by option in the datatable square brackets. Then I call the function. But when you normally would do a group by in datatable, you're calling individual columns. But if you want to use a non-standard function that's not sum or mean or something like that, you have to call the .sd object, which is a special grouped object and that respects the grouping of the data table. And then st is within distance is meant to be called either on an SF object or a geometry column. So I extract the geometry column from the .sd part of the grouped data table. Our operation now runs in fewer minutes. And this matters if you're running this often. If each group was small enough for st is within distance. So at this point, I've realized I needed an alternative for st is within distance. It just wasn't cutting it. So I turned to rfast. This is a package which has rewritten a bunch of base R functions to be faster. And it lives up to the name, including a function called dist with a capital D. This works pretty well, and it is fast. Until you get to 46,342 rows. And I had to dig into why. So I looked in the C++ code, and I saw this function which computes the number of calculations that will be needed. It's returning an integer. And that's the problem. Now remember, integers in R are 32 bits. We saw before that we need to make n times n minus 1 divided by 2 calculations. In order to figure out this number, we first need to compute n times n minus 1 in memory. So at 46,342, this comes out to be 2,147,534,622. And this, you could be thinking, is this bigger than a 32-bit integer? But 2 to the 32 minus 1 is bigger than this number. So what's the issue? That's because we use one of the bits for the sign to tell us if the number is positive or negative. So we really only have 2 to the 31 minus 1, which is smaller than our number. So we need a bigger integer in C++. This is where our XLNT comes into play. It's not a 64-bit integer, but it's the biggest integer the machine can handle, which with most modern machines is 64 bits. So I made a change of the code from this first function returning integers to the second function returning XLNT. I made a pull request, but it hasn't been accepted yet because they asked me a question and I didn't notice that until last week. So hopefully this pull request will go through soon. So then I talked to Brian Lewis, and he has a package called TCore that's going to be on CRAN soon, hopefully. It's based on IRLBA, and it's really designed for computing threshold correlation matrices, but he told me it can identify points that are within a certain distance of each other. So I do this for one cell. I convert the SF object into a matrix using ST coordinates, and I pipe it into tdist. And tdist can work in parallel if you register a parallel front end first. And I run this, and it returns the indices of the rows that are close together and the distance. I then iterated over our data table to do this to each of the cells individually. It's similar code to before. I get the coordinates as x, y, I drop the geometry, I make it a data table. I then iterate over and pass the matrix version of the group.sd object into tdist. Now this is great, but it relies on the sparsity of the answer. If there's too many rows that are close to each other, this slows down. So I couldn't count on this always being fast. So I then thought about Torch. This is essentially a matrix algebra library on a GPU. It's pretty new in R, and the R package is just R and C++. It doesn't rely on Python. So I was pretty excited about this. So I turn the geom object into a matrix using ST coordinates, and I turn that into a tensor, and I tell it to be on the GPU by saying device equals CUDA. I then call nnf pdist, and this returns the pairwise distances. This was unbelievably fast. For 37,000 rows, it finished in 0.003 seconds. That's amazing. But my GPU only has 11 gigabytes of memory, so it's easy to blow through that and crash once you get past about 60,000 rows. And not everyone has a GPU, and it takes time to load the data onto the GPU for each group, and then extract the results, and then clear the GPU memory again for each group. So there's a lot of overhead. So I then said, I need some custom code. So I huddled together with a few friends, Michael Bagelmacher, Kaz Sakamoto, and we came up with this algorithm. You first sort the data according to one dimension only, the X dimension. You then do a double for loop. You go one row at a time and then do the inner for loop comparing all the subsequent rows. You don't look backwards because you've done that already, you just look forwards. You first compute the distance along the x-axis, x1 minus x2. If that is greater than the threshold, by the triangle inequality, that means the generalized distance of all the dimensions has to be bigger than the threshold also. So you know you failed the threshold. But the bonus is that since your data are sorted according to this x-axis, you can then break out of the inner loop and skip all the subsequent points because they're sorted, all the other points are going to be farther away, and you get to get rid of all those computations for that round of the outer loop. So you save a lot of time. If that passes the test, you then compute the generalized squared distance. You don't compute distance because that involves a square root, which is costly. You compute the distance, the square distance. And that's on all the dimensions. You do it generalized for all the dimensions. And this could be more than 2 dimensions. It could be a generalized distance. Now, if that distance calculation fails, you skip it. If it passes, you then take the square root and you keep track of the indices. Doing this in R, we first allocate an array for the indices and another one for the distances. I probably could have made them one array, but this was just quick and easy. I then do a double for loop, and if your eyes aren't burning, you can see it's doing exactly what the algorithm says. You compare the x dimension first, and if that's greater than the threshold, you break out of the inner loop. If it's not, you compare the square distance. If that's good, you take the square root and make note of the indices and the distance. Running this on a single cell, it finishes 3,000 rows in about a second, 18,000 rows in 21 seconds, and 37,000 rows in 70 seconds. And part of the slowness of that is allocating the array, and there is probably a better way to allocate that array. But this seems manageable, So I'm using group by and group map to iterate over all the cells and do them individually. But all those individual timings could really add up and slow things down. And I can't really do it in parallel because that memory inefficiency could really hurt us, because when you do it in parallel, you could really inflate the memory. I needed to go faster. This still wasn't good enough for me. So I turned to Rcpp, which lets you write R-like C++ code. This is the same function written in C++, which is more verbose. The first key thing I do is, instead of pre-allocating an array for all the indices, I make a zero-length array just to keep the indices and the distances. And as I add values, I can grow the vectors. And growing a vector in C++ is much more memory efficient than doing it in R. So we're not going to pay a penalty for that. I do the double for loop, which is much faster in C++, and I use armadillo to do the matrix calculations. I first check the x dimension. I break out of the inner loop if that doesn't work. I then compute the generalized square distance. If that works, I take the square root and I push back my vectors. I make an adjustment because C++ starts counting at 0, and I return the objects as a data frame. I call this on an individual cell. For 3,000 rows, it finishes in 0.05 seconds. For 18,000 rows, it finishes in half a second. And for 37,000 rows, it finishes in 1.3 seconds. This was an insane speed up. I didn't even do anything in parallel in C++. So you can see that the C++ code is going to, as you grow your data, is going to be much, much, much faster. So let's do this for all the different cells. We get the XY data, we drop the geometry, we make it a data table. The data need to be sorted. So I use set key in data table, and that sorts the data, and I sort it according to the first dimension. I then call our function for each of the groups by using by. I say .sd calls, so I convert just the xy into a matrix, and I call my function. I get this beautiful data table back with my answers. For the entire data set, it took about 30 seconds. And I've tested this on millions of rows, and it still stays about 30 seconds. We went from cannot finish to finishing in hours, maybe, to minutes, to seconds. And this really matters when you're running this algorithm hourly. This really matters getting it down to seconds timing. And we did this by splitting the data into smaller pieces, using a smarter algorithm, and writing compiled code. And that made it a solvable problem by following these 3 steps. Thank you very much.